recording. Okay, now we started recording the session, and today we will discuss we will finish the three-phase fault. And remember that we only in chapter 7 we will only discuss the three-phase fault, but in details. I mean how to calculate. But if I ask you, for example, in the final exam, that draw, for example, a single phase to ground, double line to ground, you will draw, of course, this one, as you can see on the screen here. So this is what the first one. What's this? So this is a single phase because it's connected only to one phase to ground. And this box here, do you know this box is what? What's this box?
Fuse? Oh,
No,
protection.
impedance. Impedance could be impedance. Could be the impedance of a tractor, for example. A tractor, for example, moving, and there touches one of the ground. So this will be the resistance of the tractor. Okay. Double phase. So if I ask you to draw a double phase to ground, double line to line, these are the type of short questions. Would be three phase. This is not three phase connected, but through what? Through impedance. Also three phase. Maybe there is a tree, for example, instead of to ground. So this could be to ground. This could be zero. The impedance could be zero. If the resistance is neglected, all these will be connected down to ground. And we study this one here. If you look here also on the line to line fault, so the line touches another line. The current in all the current will flow through these, and almost zero current will flow in phase that is not touching the ground. Why? Because these are two fault. They touch each other, so there's a short circuit happens here. So all the current will flow through these two lines. Similar for this one here. Most of the current, of course, the current will flow on the phase that touches the ground. It's like sink. All the current will flow to the sink. Okay. All right. Now, if a bird, for example, why a bird can stand on one of these lines? If I draw a bird here, for example, why you can? Okay, this is a bird. It can. Why? It can.
Because the bird is not connected to the ground.
Because the bird is not connected to the ground. But if the bird touches these two by the wings, for example, then it will short. Actually, it will not short, but it will disappear for a while. So these are very extremely extra high voltage. So it will just be grilled and disappear. Okay. Disappeared. Why? Because it's a bird will burn, of course. Touches here, of course, will be affected by the wings. Touches two lines, but these lines are really separated far. The spacing between these lines is not short; it's long. Okay. Now we discussed the bus impedance matrix, but remember now we do not determine the bus impedance matrix directly from the system. What do we get from the system directly is Y bus, is the Y, and then we invert Y, we get Z. Okay, so this is none. This is what we determine from the system. We do not determine Z. Determine Y bus, and then inversion of Y bus will give us this Z. So this Z11 is the Thevenin impedance of bus number 1. Z22 is the Thevenin impedance of bus number 2, and so on. So capital N here means the number of buses. Okay. And the last time we reached to this slide here, that the voltage we discussed about the voltage, how to determine the current. This is what we're interested in. The current becomes high at the fault. That's why we are interested to find the current. Then we can set the circuit breakers. So when there is a fault current, you remember now the circuit breaker closes and then opens, automatic. Why? Maybe the fault disappeared. The fault maybe it goes away. Maybe the tractor just touches and leave and go on. So there is a fault at the beginning, high current, and then disappeared. The fault cleared away. Then the circuit breakers open and closes, recloses again. If the fault, and then opens. If the fault is still there, opens and then closes again. If the fault is there, then just the circuit breaker opens. When the circuit breaker opens, there's no current will flow. So this will protect the equipments. It will protect the transformers, will protect the transmission lines, the buses, and so on. Okay, so this is what happens here. If there is any fault, the circuit breaker open to clear the fault, so the current will be zero, not be high as we are calculating here, and then recloses again, and then opens. A very short period, maybe just 2-3 cycles, 5 cycles. Okay, open and closes. Then also from the fault current, what is the advantage? And here we can set the circuit breaker limit. The circuit breaker, when will the circuit breaker open? So and also the specification of the circuit breakers. Therefore, we need to calculate the fault current. Okay, so the calculation of the fault current here will be VF, the fault voltage. And what's the fault voltage? It's just pre-fault. We call pre-fault voltage because the fault voltage is 0. But we are calculating now the current. So we use the pre-fault voltage at the bus. So if you run load flow at the beginning and you determine the voltage at the bus, these we call them VF. Okay, the pre-fault voltage. So VF means the pre-fault voltage. Just before the fault, the voltage at the bus may be 1 per unit or 1.05 per unit. That's what we use, and over ZNN. Okay, ZNN, which is the Thevenin impedance of bus number N, where the fault happens. Okay, so this is N, small n, this will be small n. This is 1, this will be 1, 1, 2, 2, etc. Okay. And this one here, here is EK. What is EK? Is what will be the voltage at bus number K when there is a fault at bus number N. Okay, a fault happens at bus number N, how it will affect other buses. So what will be the voltage? Of course, the voltage will be lower. Then it was maybe 1 per unit, then it will be maybe 0.8, 7.9, etc. And this depends on what you think. How severely the buses will be affected. I'm asking you now. Depends on what? Depends on how close the buses to the faulted bus. If they are very close, of course, they will be highly affected. The voltage will go down. If they are far from the faulted bus, there will be just a negligible effect or will be no effect. Okay, so it depends on how close they are to the bus. Okay, so this will be, and this is the voltage at the bus number K when a fault happens at bus number N. So what you will use ZKN, and this is one minus because we're using this one here. So we can simplify this one here into this. Okay, so we add. So that is the formula. So you will use this formula in your cheat sheet. Okay, so please make sure that, or this one is the same thing here. And remember now, VF is what is the pre-fault voltage at what bus? At the faulted bus, of course. So in our case here will be VF at bus number N. Okay, at bus number N, because the fault happens at bus number N. And we want to find the voltage at bus number K. So you will use the volts here of bus number N, not K. Okay. In K, you will only use this part. ZKN. What's ZKN? It will be from these, which is the off-diagonal elements. For example, 1N, 3N, okay. 1K, 2K, 3K. The 1N, KN, KN. All right. We discussed this also. Determine determine the 2x2 positive sequence bus impedance matrix. How do we know it's 2x2? Because these are two buses, bus number 1 and bus number 2. So therefore, the bus impedance matrix will be 2x2. How we get it? We get it from the Y bus. And therefore, this terminology here for a bolted three-phase short circuit, it means that it has no impedance in between. It's straight to ground. We call it bolted three-phase short circuit. So it's to ground. So there is no impedance between the line and the ground. And then we use Z bus to calculate the subtransient fault current. And why we are interested in subtransient fault current, not in transient? Why? Why we are interested in subtransient fault current?
Because this is the worst current.
The worst current. Okay, صح صحيح معنا حلوين. So the subtransient fault current, remember now, the subtransient reactance is much lower than the transient reactance. Is lower than the synchronous reactance. This is where we use in the steady state, we use X. And this is the worst case. And then if we want the transient, so we want to determine the current, the behavior of the current, also use this one. Okay, the transient. So this is the worst case because this is lower, much lower. The subtransient reactance is much lower than the others. Much lower, it means that the current is high. Why? Because V over X equals I. So I equals V over X. And this X here, X is lower. Okay, so the lowest, this will become high, where this becomes low. Okay. And then also this repeat part B for what at bus number 2. You know, here bus number 1 and bus number 2. So these are the type of questions will be in the final exam. And I encourage you please to study this one, to not miss these type of questions. All right, so it's 2 by 2. So we determine now, because there are two buses, and we know how to determine the nodal analysis. For the nodal analysis, we determine y. So this is y11, y22, and this will be, remember now, y12 equals y21. Okay, and these are equal. And you put the negative sign. Don't forget the negative sign. And then you will use the inversion. You are required to know how to invert 2 by 2 matrix. Okay, so please, whether you do it by your calculator or you do it by hand, it's up to you. Okay. Okay, so you will determine 2 by 2 matrices, the inversion of 2 matrices. So please use your calculator. Try to use these tools. So try to use, or if you don't have a calculator, then you will use by hand. Now we are interested. Now you see here. Okay. Then we get the Y bus, the Z bus. This now, if the fault happens at bus number 1, which is this the case, then we use Z11. So we use this part, and we use it here. And this VF is given as 1.05. Okay? 1.05 is given from where? It's given in the bus here, because this is the same example that we used, and it was operating at 1.05 per unit. Here we are. The pre-fault voltage is 1.05, and pre-fault load current is neglected. So this is given 1.05. Just very simple. So the whole problem is just to find how to find Y bus. Focus on this, how to find Y bus, and then you invert it to find Z bus. And then this is the fault current. Very simple, straightforward. And don't forget this negative sign. It comes from the J, which is here on the denominator. So to bring it up, it will be minus J. And this is per unit. You see, that's 9 ampere, not 9 kilo ampere, not 9. So this is in per unit, and it depends on the base. So this is very, very high. You see, it's 9 per unit, very high current. Okay. Now what we want also to find E1 because happy, so it will be 0. That's why Z11 over Z12. But if you want E2, what does it mean, E2? I want to hear from you. What does E2 mean? What does E2? Oh, I need to find the names. I need to find your names. What does E2 mean? Yes, yeah, Mohammed Murtaza.
E2 means the voltage at the bus 2 if the fault happened at bus 1.
Very good. Okay, so we use this formula. Okay, and we know now how we determine the formula. Okay. E1 we use Z11 here, so this will become 0, of course. E1 will be 0. E1 will be 0. Why? Because the fault happens at E1. And we differentiate now E from VF. This VF is not 0. VF is a pre-fault voltage. Although we write VF, it's a pre-fault voltage, which is 1.05. That's from the load flow. So we want to differentiate E with the V, pre-fault voltage. So E2 will be Z21, Z11. Okay, so then we'll just get this one. See now E2 becomes very small, 0.6. It was maybe 1 per unit, but now becomes 0.634 per unit. Becomes lower. So this is the idea that you want. And then if you want the current to the fault for the transmission line, the current to the fault from the transmission line obtained the voltage drop from bus 2 is from bus 2 to what? Remember now the fault happens at bus number 2. And we want to find the current that comes from bus 2. All the current now will come to the fault. Okay? The current was bus 2 will also go to bus 1. So the weakest point, that's the weakest point, the lowest, because the voltage drops to 0. Therefore, all the current will flow to that bus. So this is the current flows from bus 2 to the faulted bus, which is bus number 1. So we call it I21, comes from 2 to 1. I12 means from 1 to 2. So this is from 2 to 1. And then very simple, so E2 minus E1. So this is the circuits now becomes Ohm's law. E2 minus E1, not E1 minus E2, E2 minus E1. And E1 is 0. Over all the impedance between 1 and 2, which is what was the line, transformer 1 and transformer 2. Then we get this number. IT1 divided, okay? Okay. Now, if the current happens at bus number 2, if the fault happens at bus number 2, very simple, VF over Z22, you see, straightforward, as long as you know how you determine Z from Y bus. And then you will get this fault current. Then what we want E2 straightforward will be 0. Because the fault happens at bus number 2. And then you will use this formula here. E1, then it will be 0.7. And this is the way to check also your answer. It's lower than 1. So the voltage drops at the bus. You see now how the importance of Z bus and how to determine from Y. And then I12. Now see, it is not to 1. Y12 means from 1 to 2. So therefore, you will be to E1 minus E2. So this will be over 9 transformer 2 transformer 1. So what will be the current? So this will be minus J. And this negative J here is the angle, this, because of this J here at the denominator. Now this concludes section 3 and 4 from your textbook. Okay? And which is the part which is part of the topics that covered in this course. Now we will go back to chapter 6 now, the power flow. Okay? I will stop unless you have a question. I will stop this one and go to chapter 6, the power flow.